All right. We're going to do a new reaction that makes carboxylic acid and review reactions that deprotect alcohols. And then an alcohol reacts with a carboxylic acid to make an ester. That's another Fischer esterification. Fischer. We did an activity on that earlier today. And this one is a review of DHP deprotection. Deprotection. Found somewhere in chapter 10 in the DHP area. And this is new. But is it? New, but really, is it new? It's not really. It's just like the reaction with aldehydes and ketones, everybody. So you've got a spectator you can cross off. The whole MGBR deal is a spectator. It's the cation. This is the anion right there. You can do that right there. Cross off the spectator. Put the charge on the anion. And ladies and gentlemen, you don't want to draw that nasty little group. Not even little, it's big. So we're going to do an R on it. And that anion is attracted to the very positive carbonyl of carbon dioxide. This is a fun reaction to do if you ever have the opportunity to do this reaction. You go to Meyer and buy some dry ice, which is pure carbon dioxide. You get a solution set up with your molecule in it, maybe in hexane or something like that. You drop in the dry ice and let it bubble away. The bubbling is basically, it's just evaporating. It's okay, you're using a huge excess. Some of the stuff that doesn't bubble away reacts right here. And you've got your R attached to a new carbonyl with an O- here. And I think you're really liking this mechanism because you're saying, wow, it's done, almost. This is RCO2H up here. This is RCO2- here. Where's the extra H come from? You guessed it. HCl. Done. Great way to make a carboxylic acid that has one extra carbon compared to the Grignard or organolithium that you started with, right? We can always use organolithiums in the place of Grignard. This is a Grignard. And you got a new carboxylic acid that has a new carbon here. And DHP deprotection, I'm going to do another R this time. All the way down here. That piece doesn't change in this reaction. R prime. And we're going to get our colors going here because red first, baby blue second. And we got to make something leave here. You can think of this as the leaving group here, or this is the leaving group here. I don't think it matters which. Does not. Either way, this is the O that has to go away from, either go away from this carbon or go away from this carbon. Either way. So you better protonate it. When you want something to go away and it's got an oxygen in it, often we protonate it. And here it's protonated. Oh, let's make it go away while we're here. Yeah. Stick with green reaction arrows. And make it go away with baby blue. Now, this decision was not taken lightly. If I have a cation that can resonate with a lone pair on the other oxygen, that's a much better cation than this primary cation here, which I don't even like primary cations. You know that, right? But this primary cation can resonate, so I don't care that it's primary anymore at all. And here is your lovely cation that can resonate. There's a lone pair it can resonate with. And the other piece is pretty simple, isn't it? It's that. So let's just finish the side reaction off. A good question is, when does he want the mechanism for the side product? And when doesn't he? That's a good question. If I give you the side product, I think I want the mechanism for it too. Yeah, it's nice of me to give you the side product as a clue, but as a cost, you also have to show me where it comes from. So I don't think any of this is like revolutionary or anything. We're almost there, aren't we? Water had to be used for some reason, right? It's over the arrow. And finally, the sulfate ion is going to come to bear. Grab the H. Sigma becomes lone pair. Done. That guy becomes that guy. EHPD protection. Cool stuff. Fischer esterification. Pretty darn cool as well. Yeah. Fischer esterification. We have to make this bond, don't we? Right here. That has to be made. That's the O. That's the carbonyl. They're not interested in each other. How do I make it more interested in the carbonyl? Talk to me. Protonate the carbonyl. Step 1, protonate the carbonyl. Step 2, attack with the alcohol. Oh, I don't know how that happens. There we go. Lone pair on the alcohol. No, blue lone pair. And I'm going to scribble off the H while I'm here and draw it, because step 3, it's coming off. Baby blue. Lone pair attacks that activated carbonyl you just made. Sigma, pi becomes sigma. No, stop. Pi becomes lone pair. That'll neutralize the oxonium. Let's go here. Oh, sulfate ion you just made, right? So I'm going to draw an organic product there and sulfate here. Sulfate's going to neutralize your new oxonium with a third color. How about green? No. We used green already. I don't like it. Purple. Arrows are purple. Oh, wow. I'm running out of colors. Light pink. There. You've made this product, except it's not this product. You've made this product. It's got an OH up there. And it's got another OH on the same carbonyl. Yep. And we got to make that. Here's your new bond you made. Got to make that into this. So clearly we have to lose an H from one side and an OH from the other. Acid catalyzed dehydration. How do you know it's acid catalyzed? Because in this mechanism I've got an acid. So acid makes leaving group leave. pick one of the O's to be a leaving group, put your acid near it. Conjugate base grabs H from the other O. We better make the leaving group happen first. Lone pair protonates first to make it a better leaving group. Then you can make the leaving happen. Baby blue. Lone pair grabs H. Sigma becomes pi. Leaving group does what leaving groups do. It leaves. And there's the whole story. And that's the end of today's lectures.